Senhoras e senhores, o Instituto de Estudos Avançados de São Carlos, da Universidade de São Paulo, o Programa Internacional de Estudos e Projetos para a América Latina, o PEPAL, Ford Foundation, tem a satisfação de receber a todos nessa solenidade de abertura do workshop Materiais Cerâmicos, Educação, Desenvolvimento, Oportunidades e Parcerias. Nós gostaríamos de agradecer antecipadamente a presença de todos e convidar para a formação da mesa as seguintes autoridades. Professor Dr. Sérgio Mascarenhas, ele que é o coordenador do Instituto de Estudos Avançados e diretor do PEPAL. Professor Dr. Targino de Araújo Filho, pró-reitor de extensão da Universidade Federal de São Carlos, representando neste ato o seu reitor magnífico José Rubens Rebelato. Professora doutora Ivone Mascarenhas, ela que é a decano do Conselho Universitário da Universidade de São Paulo e diretora do Instituto de Física de São Carlos. Professor doutor Woodrow Nelson Lopes Roma, vice-diretor da Escola de Engenharia de São Carlos, neste ato representando o seu diretor Jurandir Polvinero. Professor Dr. Hildebrando Munhoz Rodrigues, diretor do Instituto de Ciências Matemáticas de São Carlos. Professor Dr. Silvio Crestana, ex-chefe do CNPD da Embrapa, diretor do laboratório da Embrapa no exterior, o LABEX. Professor Dr. Umbelino Gomes, superintendente da Fundação Universidade do Rio Grande do Norte. Os nossos palestrantes, professores Anthony Sheehan, da Universidade de Santa Bárbara, na Califórnia. Professor Hendrikus de Waal. Professor Roberto Cesário, da Universidade Sassari, na Itália. Professor Dr. John Webster, da Universidade de Connecticut. Nós gostaríamos de registrar ainda a presença dos coordenadores do workshop Materiais Cerâmicos, que é a professora Ivone Primeirano Mascarenhas, do setor de instrumentação, professor José de Anchieta Rodrigues, que é o coordenador do workshop e coordenador do setor de refratários, professor Dr. Fernando Gomes de Oliveira, do setor de abrasivos, professor Dr. Edgar Dutra Zanotto, setor de vidros, professor Dr. Anselmo Ortega Bosque, do revestimento cerâmicos, e o professor Dr. Rui Alberto Correia Otafim, que é o diretor do CETEPE e do setor de isoladores. Agradecendo a presença de todos, nós passamos a palavra ao professor Mascarenhas para a abertura oficial desta cerimônia.
Muito bom dia, apesar da chuva. É uma satisfação tê-los aqui. Essa é a primeira atividade internacional do nosso programa e do IEA. Uma grande honra estar aqui com vocês. I want to thank the presence of all foreign colleagues here. I'm sorry I'll have to speak in Portuguese after my first phrases, but it's a pleasure to have you here. E também me gostaria muito de agradecer a los colegas de Espanha, de América Latina, e hablarles dos frases, al menos em portunhol. E é uma grande satisfação de tê-los acá. E é claro que para nós outros de Brasil a presença de América Latina é fundamental para que nós outros possamos unidos caminhar para um desenvolvimento científico e tecnológico que nos libere destas cadenas de colonização científica e tecnológica que temos em América Latina. E les agradeço muito por haver venido, apesar da lluvia também. De agora em diante eu vou falar em português com o sotaque carioca, Diz a Ivone que ninguém vai entender nada por causa do sotaque carioca. Tudo bem. Isso me lembra uma piada que aconteceu comigo na Argentina. Fiz uma palestra em Portunhol e um grande amigo meu, que é o professor Jorge Sábato, me disse depois da palestra: Sérgio, é a primeira vez que eu consegui entender português completamente. Então, foi uma grande frustração. Bem, eu gostaria de agradecer a todos os meus colegas da Comissão de Coordenação já nomeados, em particular o nosso secretário, o nosso coordenador, que foi o professor Anchieta, que realmente nos ajudou muito. Mas eu gostaria de dizer que a ideia desse workshop na área de cerâmica partiu da Ivone Mascarenhas. Foi ela que fez a sugestão inicial, lembrando que São Carlos é um polo muito forte de cerâmicas, vidros, e que, portanto, nós poderíamos começar muito bem essas atividades através. Então, eu agradeço muito a ela ter lembrado que essa área deveria ser uma área de grande motivação. Quero agradecer a Ford Foundation, sobretudo na pessoa da doutora John Dessing, que era, então, a diretora-geral da Ford Foundation nos Estados Unidos para a América Latina, o Dr. Nigel Brook, que é o diretor da Ford Foundation no Brasil. Queria agradecer a Prefeitura do campus, na pessoa de toda a sua equipe, o professor Rocco, o professor Pimenta, e a diretoria do CETEPE, que é dirigido por um dos nossos coordenadores, o professor Rui Altafim, e todos os outros colegas de institutos de física, Instituto de Física, Instituto de Matemática, a Escola de Engenharia de São Carlos e o Instituto de Química. Agradecer ao CNPq, o Conselho Nacional de Pesquisa, na pessoa do professor Tundizi, ao SEBRAE, na pessoa do Dr. Silvio Rosa, à Embrapa, aqui representada pelo professor Silvio Crestana, que nos ajudou muito para a organização desse simpósio, que tem colaborado com o PIEPAL e com o IEA, os visitantes estrangeiros, e eu acho que não poderia também deixar de mencionar o grande apoio e a eficientíssima colaboração do nosso Mauro Barion e equipe, que organizou tudo isso que vocês estão vendo aqui, e organizou praticamente todo o programa ao longo de todos esses meses de preparação. Bem, eu gostaria de explicar a vocês, em 2 palavras, depois eu tenho uma surpresa para vocês também, mas eu gostaria de explicar em 2 palavras o que é o PIEPAL e o Instituto de Estudos Avançados e como que surgiu essa ideia. Eu não sei se agora nós viramos todos para lá ou se eu acho que talvez seja melhor passar todo mundo para lá, né? Se vocês quiserem, se os membros da mesa quiserem, espera aí, eu acho que eu estou errando uma coisa. Perdão. Algum dos membros da mesa desejaria fazer uso da palavra? Na ocasião? Então, eu agradeço a presença de todos, mas eu acho que talvez seja mais conveniente passarmos para o outro lado. Vou contar com o apoio do nosso querido professor João Fernando Gomes de Oliveira e dizer algumas palavras sobre esse programa internacional de estudos e projetos para a América Latina. A ideia desse programa veio dos problemas que nós temos no Brasil e na América Latina. E eu gostaria de passar, então, a segunda. Os problemas são, basicamente, que, face à globalização e formação de blocos políticos e econômicos, nós precisamos de colaborar para a maior integração das comunidades técnica, científica e empresarial na América Latina, de modo a assegurar efetiva atuação para a nossa sociedade. Em particular, ou a América Latina se une através da ciência e tecnologia, onde ela já tem, inclusive, uma tradição de união, ou ela vai continuar colonizada, como foi até agora. Então, isso eu considero fundamental. Com a queda do Estado-nação, com o neoliberalismo, com o qual eu absolutamente não concordo, nós perdemos toda aquela dignidade do Estado-nação que foi mencionada por um argentino dos mais ilustres que estivemos na América Latina, que é o Raul Prebisch, um economista, que foi o criador da CEPAL, da Comissão Econômica para a América Latina. Juntamente com o Celso Furtado, de agora, com o Fernando Henrique, de antigamente, e com o Jorge Sábato, que infelizmente já faleceu, se constituiu um movimento de verdadeira liberação intelectual e programática para a América Latina, que foi a CEPAL. E, na realidade, quando eu comecei essas ideias, nós íamos chamar o PIEPAL de CIEPAL, para ele ser homófono com CEPAL. Mas não foi possível, porque a ideia de centro dentro da USP é mais complexa burocraticamente. Então, nós ficamos com um Programa Internacional de Estudos e Projetos para a América Latina, que logo ganhou o apoio de todos os colegas daqui do campus, e eu novamente agradeço na figura dos diretores aqui presentes, e nós conseguimos, então, estruturar isso a nível da USP. O planejamento é através de grupos de trabalho e workshops temáticos para a preparação e integração de projetos de interesse estratégico regional para a América Latina, envolvendo empresas, universidades, centros de pesquisas, instituições governamentais e não governamentais. Aqui cabe dizer que uma das instituições que mais nos apoiou foi exatamente a Empresa Brasileira de Pesquisas Agropecuárias, na pessoa do seu presidente, que eu gostaria de mencionar aqui, Dr. Duque Portugal, e do, então, coordenador, do chefe-geral do Centro Nacional de Pesquisa e Desenvolvimento de Instrumentação Agropecuária, professor Silvio Crestano, aqui presente, que é sempre um companheiro de longa data, de lutas, ideais, sonhos, às vezes alguns pesadelos que nós temos juntos também, mas, em geral, a gente consegue resgatar essas coisas. Então, nós recebemos um apoio muito forte, mais apoio de entusiasmo do que propriamente apoio financeiro. Mas, logo depois, com o apoio de todos os diretores do campus e da prefeitura, conseguimos do reitor da Universidade de São Paulo, reitor agora, professor Fava de Moraes, uma garantia muito forte, que foi a construção de um prédio para o Instituto de Estudos Avançados aqui na USP, que está pronto. Em 10 meses, ele foi feito e foi inaugurado no dia 20 de novembro, e, eventualmente, nós levaremos vocês a esse prédio. Em cima do prédio, no segundo andar, tem uma rádio e tem uma estação de televisão também, e nós pretendemos integrar tudo isso, e mais a rede de computadores já interligada com fibra ótica, na formação de uma rede para a América Latina de atividades em ciência e tecnologia. Bem, eu gostaria de mostrar um último transparência, que expressa, recebemos também apoio, naturalmente, do SEBRAE, que é o organismo brasileiro da pequena e microempresa, na pessoa do Dr. Silvio Rosa. Eu gostaria de mostrar mais uma transparência só, que expressa as ideias da CEPAL, mas o apoio grande nós tivemos também da UFSCar, desde os primeiros momentos, ainda na gestão do reitor anterior da UFSCar, o professor Newton. Ele já tinham pensado nesses projetos para a América Latina e nos deram todo apoio. Não foi uma coincidência, mas um determinismo de trabalho conjunto que a maioria dos membros que cooperaram para a formação desse Congresso de Cerâmica foi exatamente da Universidade Federal, que possui um dos maiores núcleos da América Latina na área de engenharia e ciência de materiais, e com grande contato com empresas. Então, a Universidade Federal ela representa um núcleo de extrema importância para o desenvolvimento brasileiro e da América Latina. A ideia básica que provém do CEPAL na América Latina, e as ideias que sempre eu procurei perseguir, é que, na realidade, a ciência e a tecnologia, no nosso século e no próximo, estão em processo de convergência temporal. Antigamente se podia falar em ciência e tecnologia separadamente, embora ainda em muitos lugares se fale ciência básica, ciência aplicada, tecnologia, sem dar uma conotação explícita a esses termos, o fenômeno sociológico de desenvolvimento, ele é expresso nesse gráfico, que a ciência converge sobre a tecnologia. Uma descoberta no campo científico demorava antigamente 20, 30 anos para ser aproveitada pela sociedade. Mas esse tempo foi encurtando. No mesmo ano que o laser foi inventado, ele foi aplicado em tecnologia, foi aplicado em empresas e deu, inclusive, uma movimentação, foi um motor econômico. Então, essa é a visão fundamental que qualquer universitário, qualquer empresário, qualquer estudante, qualquer professor tem que ter na cabeça, que essas duas setinhas aí, elas são um símbolo do progresso da humanidade em relação à interdisciplinariedade, em relação ao caminho integrado, híbrido, de ciência e tecnologia. Assim como elas estão convergindo, você não pode mais falar na profissão de físico ou de químico, ou de engenheiro ou tecnólogo, você tem que pensar num híbrido interdisciplinar que emerja dessa tendência. Aqui, no campus de São Carlos, nós vemos isso claramente em várias das ações. Na UFSCar, isso já vinha acontecendo há anos atrás, com a criação da Engenharia de Materiais e de Centro de Tecnologia Educacional e de Meio Ambiente, que realmente foi pioneira há cerca de 26, 27 anos atrás. E esse eu acho que é o ponto fundamental para nós pensarmos em... Um outro ponto fundamental de filosofia do PIEPAL, porque qualquer instituição que não tenha bases filosóficas, que não esteja fortemente assentada em objetivos claros, utópicos, mas claros, né? Essa conjunção entre a utopia do sonho e a operacionalidade da praxis, da realização, essa é a grande dificuldade que nós temos, mas, por outro lado, ela é a fonte de todo o segredo de você poder progredir no desenvolvimento científico e tecnológico. Essa ideia veio do Jorge Sabato, um outro argentino, que foi um dos maiores líderes que nós tivemos a nível mundial. Infelizmente, ele já faleceu. Ele me ajudou muito quando eu era reitor pro-tempore da Universidade Federal de São Carlos e propus a criação da Engenharia de Materiais. Então, eu chamei o Sabato, que nos ajudou muito, porque já antes disso a Argentina tinha a famosa Escola de Metalúrgia na Argentina, que foi pioneira a nível mundial. Então, o Jorge Sabato dizia que é fundamental que você tenha a interação entre município e região, universidade, centro de pesquisa, instituições educacionais e empresas. E isso foi o que se chamou o Triângulo de Sabato. Hoje, nesse simpósio, nós vemos esse triângulo realizado na prática através da presença de empresas muito importantes que estão aqui, da várias universidades da Argentina, do Brasil, da Espanha, e presença de atividades do município da região. São Carlos já criou mais de 90 microempresas de alta tecnologia, graças às atividades iniciadas pelo Parque de Alta Tecnologia, dirigido pelo professor Silvio Rosa. Eu estou procurando mostrar o embasamento que nós procuramos trazer. O intercâmbio regional, nacional e internacional, um dos objetivos básicos do PIEPAL, e nós temos vocação de áreas estratégicas aqui em São Carlos e no PIEPAL. que são os materiais, cerâmicas, polímeros, vidros, metais, solos, que é muito importante a nível da Embrapa. O professor Silvio Crestana introduziu várias técnicas de alta tecnologia no estudo de solos, como o uso de tomografia computadorizada, qual nós ouviremos aqui hoje com o professor Cesário, que foi um dos introdutores desta técnica, também para vários materiais, informática, instrumentação, automação, imagens, estruturologia e biotecnologia, inteligência artificial, tecnologia educacional, ecologia, meio ambiente, tecnologias avançadas na agropecuária. Todas essas são áreas que já estão, que têm núcleos muito fortes aqui em São Carlos. Eu vou exemplificar com uma coisa muito nova que está acontecendo no Instituto de Estudos Avançados, que eu estou coordenando e que eu considero da maior importância. Na universidade, nós temos duas grandes dívidas sociais. Uma dívida com relação ao desenvolvimento econômico dos nossos países. Isso é, relação universidade-empresa, formação de ciência para a sociedade, saída da Torre de Marfim, extensão de serviços à comunidade. Esse é um lado. Do outro lado, nós temos a dívida social com a educação, sobretudo primária, secundária e com a educação técnica. Então, o PEPAL e o IAA têm essas duas grandes missões. Do lado da relação com universidade, empresa, tecnologia, esse simpósio é a primeira atividade. Do lado da educação, nós estamos com um outro projeto, também apoiado pela Ford Foundation, que vai envolver a Estação Ciência, que é um museu de ciência de São Paulo, o Centro de Divulgação Científica e Cultural de São Carlos, o CDCC, que desenvolveram projetos para ensino de ciências e que está em andamento, no caso do CDCC, há 18 anos, no caso da Estação Ciência de São Paulo, há 10 anos. E esses dois projetos são para resgatar, dentro da cultura brasileira e latino-americana, esperamos, a presença de ciência e tecnologia como parte da nossa cultura. Não apenas futebol e carnaval, ou tango, mas também a ciência e tecnologia, de preferência junto com ciência e arte, junto com música, etc. Então, nós temos esses projetos que já estão apoiados pela Ford Foundation, estamos preparando um grande projeto para o Banco Interamericano de Desenvolvimento, que vai envolver todos os centros de ciência, de ensino de ciência da América Latina. Há pouco tempo nós estivemos em Córdoba, na Argentina, que tem um grande líder do ensino e da educação da física na América Latina, que é o professor Mastegui, que, juntamente com o Sábato, escreveram livros importantíssimos de ensino. E nós estamos, então, procurando desenvolver esse projeto integrado. São as duas janelas, né? E nós temos uma missão muito importante para tentar pagar um pouco dessa dívida social. Acabou? Bem, então, eu acho que terminou uma pequena explicação. Eu peço desculpa, I'm sorry to the foreign colleagues that I cannot explain all this in English or Portunhol, but I think this will give you an idea of what's PEPAL, what's the Instituto de Estudos Avançados da USP. Okay, now we had invited Professor Tundizi, the president of the National Research Council of Brazil, to speak in the ceremony. He could not come because he's fighting for the money in Brasilia of the budget. So I told him, stay there, don't come. Então, o professor Tundizi não pôde vir. Também o professor Pérez está muito empenhado em várias atividades, não pôde vir. E eu, então, fiquei pensando, puxa, mas então duas pessoas importantes que iam falar na abertura não estão aí. Como é que eu vou resolver essa situação? Se coloquem na minha situação, tá certo, de coordenador, então, uns dias antes acontece isso, não vem. Bom, eu tenho que arrumar uma solução criativa para esse problema e que seja, ao mesmo tempo, representativa de toda essa filosofia, né? Bom, primeiro, nós criamos aqui também um núcleo de linguagens naturais, no IAA, com um núcleo interdisciplinar de linguagens computacionais, e nós vamos ser a sede, preparação do dicionário para a internet disso, dentro do IEA, com colaboração do Instituto de Ciências Matemáticas de São Carlos e do Instituto de Física. E esse é um projeto importante. Mas qual é a outra? Já ainda que não tem ainda essa linguagem natural de computador, né? Que, aliás, é uma linguagem meia fria, né? Qual é a outra linguagem universal que eu poderia usar nessa palestra de abertura, em lugar dessas grandes personalidades? Então, obviamente, é a linguagem da arte, é a linguagem da música. E nós temos no nosso comitê uma pessoa extraordinária, que é o professor João Fernando Gomes de Oliveira, que, além de cientista, é um grande músico. Então, ontem à noite, eu falei com ele, o nome dele, cá entre nós, o apelido é Moringa. Eu disse, Moringa, o que nós vamos fazer? Eu acho que você vai ter que falar na linguagem universal da música para o Tony Cheetham, para a professora Reca, para o professor Mário, todos os colegas, o professor Deval, que não fala, o professor Cesário fala português, não se aplica para ele, mas gosta muito de música. Então, eu convidei o Moringa, se ele poderia fazer o discurso de abertura, um discurso feito em notas musicais, com alguma música brasileira. Então, ele, de impromptu, não é o impromptu do Chopin, é o impromptu do João Fernando Gomes de Oliveira, ele resolveu tocar aqui para nós, e ele é que vai fazer, então, a apresentação de abertura desse congresso, no lugar do presidente do CNPq, do presidente da FAPESP, etc. Então, está convidado para falar essa linguagem universal que é a música. E nos dizer antes, talvez, explicar o que ele vai fazer.
Professor,
Acho que não está funcionando isso.
está sim.
Tá? Está funcionando?
Aumentando o volume do microfone errado. Vamos trocar então?
Vamos trocar? Vocês veem que tudo aqui... Acho que você pode trocar o microfone aí? Dá uma batidinha aí, Murilo. Já está? Já está, Murilo.
Alô, alô. Ele achou. É esse aí, então.
Obrigado.
Esse botão certo. Com essa ideia do professor Mascarenhas, alô, agora o outro se abaixa. Abaixou de novo errado. Era aquele. Alô. Tudo bem, esquece. Bom, a ideia do professor Mascarenhas, esse aqui tá alto, hein? Abaixa tudo agora.
Ô Moringa, você quer dar uma explicação fora daquela... O Moringa disse que ele escolheu o samba de uma nota só, porque cerâmica é uma nota só, com as 6 áreas em volta dela, harmonicamente colocadas, fazendo, então, também uma estrutura, não só melódica, mas uma composição. Então, a tirada filosófica que ele deu de samba de uma nota só foi a de união na diversidade interdisciplinar. E, como sempre, ele é super criativo, né? E bolou isso aí. Então, eu acho que, com isso, nós tivemos, acho que um dos primeiros simpósios aqui no Brasil, em que o speaker, a pessoa que falou uma linguagem brasileira e que todos entendem. Eu agradeço muito a presença de vocês e, imediatamente, vamos começar. Aliás, eu gostaria só de fazer um outro anúncio. Estou vendo aqui a presença do Silvio Crestana e todo esse esforço do PEPAL, do IAA, surgiu muito de equipe que estavam trabalhando juntos, tanto aqui na USP como na Embrapa. E eu queria, com a permissão do Silvio, anunciar que ele foi escolhido pela Embrapa, que é a maior instituição de pesquisas do Brasil, em todas as áreas. Ele foi escolhido num concurso nacional para ser o novo diretor do laboratório da Embrapa no exterior, nos Estados Unidos, em Washington, fazendo um programa pioneiro em que o Brasil vai ter um laboratório de pesquisas no exterior para resolver problemas brasileiros num horizonte menor de pesquisa e com uma antenagem muito forte em relação aos problemas de ciência e tecnologia. Esse é um bom exemplo para nós da América Latina e o professor Silvio Crestani, então, honra muito essa... E ele tem sido um dos estimuladores do PEPAL, do IAA. Então, foi uma notícia também muito importante para nós da comunidade científica, que vamos ter um embaixador em Washington de ciência e tecnologia. Parabéns, Silvio. Ok. Então, nós vamos começar imediatamente com a primeira palestra, que será a professora Ivone vai apresentar o Dr. Chitan, que vai dar a primeira palestra, então.
Well, first of all, I would like to thank Tony to have agreed to come and to give his important contribution to our workshop. I want to tell you, besides all the titles and the long experience that Tony has on this field, to tell you why he was invited. Some time ago, I decided that I was only used to work with single crystals. And I felt that single crystals are marvelous. But many substances don't crystallize beautifully as single crystals. So I started to work on with powders. After some years trying to establish this technique in our group, we had the idea of organizing another workshop. This was in '92. And then I just have met, I was more familiar with Ray Young from Georgia Tech. And he practically made the scientific organization of that workshop. So he invited Tony and von Drill, another important scientist from the United States, to come and give the workshop. The presence of Tony was really very fundamental for that, in that occasion. His warm attitude towards all our students that were some more prepared, others not so well familiar with the topics, but he had a very warm relationship with everyone. And we keep a very good memory of these few days that he spent with us. Later on, I had a student who became more familiar with the topic of powders, powder crystallography, and he accepted him to do a part of his PhD, as a matter of fact, the complete thesis in his laboratory at Santa Barbara. So this relationship was strengthened also with this cooperation that is already finishing with the PhD thesis practically ready for presentation in Brazil. So when we had this idea of inviting someone, my idea was that Tony was someone that should come. This may be a minor part of his scientific curriculum, but for us it's very important, and I think this is an occasion which we can thank him for this important contribution that we had, that we received from him. As this may not look so important regarding all the other scientific achievements of Professor Tony Sheaton, I have to inform you that he had his PhD at the University of Oxford in 1971, and he was a member of the chemistry faculty of Oxford until 1991. Then he moved to California, to Santa Barbara, to become the professor in the materials and chemistry departments, and in 1992, director of the newly created Material Research Laboratory. Since 1986, he has also held the chair in solid-state chemistry at the Royal Institution in London. His research on the chemistry of materials has been recognized by a number of awards, including Corday Morgan Medal in 1982, the Medal of Solid-State Chemistry in 1988, Medal of Structural Chemistry in 1996, and the Royal Society of Chemistry, election to the Fellowship for the Royal Society. This was, as everybody knows, the more prestigious scientific society in all the world. And now, and he was also elected as foreign member for the Pakistan Academy of Science in 1997. At this moment, he is enjoying a sabbatical in a very nice place. I think all of us envy him also for that. He's in Paris, but keeping close contact with all his friends all over the world. He travels a lot. This is just one of the many travels that he does each year. So with this brief introduction, I pass the microphone to Tony.
Thank you, Ivone. Let me see. Is it possible maybe for us to move this off? And then, just to move it back. Well, thank you very much for those kind words, Ivone. I don't even recognize myself when you introduce me. And I'd like to say what a tremendous pleasure it is to have this opportunity to come back to Brazil. And you're wrong on one point, which is this is not a small thing for me. It's something that I very much appreciate. It's an honor to be invited to this meeting. And I'm very excited to be here again, in fact. So I'd like to thank you and Professor Mascarenhas for the kind of opportunity to join you. Please forgive the fact that I should be speaking in English. My Portuguese is even worse than my Spanish, but I do speak French, so if anybody wants to talk to me afterwards in French, and that is fine. So what I'm going to do, just to give a brief overview, is to talk mainly in terms of the kind of industrial interactions that we have in Santa Barbara, because that's what I, of course, know most about. So I'll tell you a little bit about how the laboratory that I run interacts with industry. I'm going to talk about, in general terms, about some of the models for such interactions, including things like the use of central facilities and national facilities. And then, inevitably, there are sometimes problems and pitfalls in this area, and we can't hide those things, and I wanted to share some of those with you. And then finally, I'm going to talk a little bit about some science, which is more comfortable for me, and just illustrate some case histories of interactions that we've enjoyed with industrial laboratories while we've been working in Santa Barbara. So the center that I run in Santa Barbara, we call it the Materials Research Laboratory, and it's funded by the National Science Foundation, and it has a number of elements. It has a scientific program, which has 4 main themes, and I'm not going to talk about those this morning. These are the 4 main themes of the laboratory. But over and above that, as a large center for interdisciplinary research, and we have faculty from about 8 different departments, roughly half of them engineers and half of them scientists. As part of that program funded by the National Science Foundation, we have to do a number of other things. We have to try and maintain central facilities, sort of state-of-the-art central facilities, both for ourselves and for others to use. We're required to have an educational outreach program to the community, which is very important for us and turns out to be very rewarding. And then we have a lot of international activities, and we run workshops as well. But over and above all of these things, there's one additional and most important element, which is what I call the technology outreach program, which is the way in which we interact with industry. And there are essentially 5 elements to that program. First of all, we have an advisory board, an industrial advisory board. And in fact, it's our only advisory board. So I don't really call it the industrial advisory board, since we don't have any other one. It's just the advisory board to the laboratory comprises a number of industrial scientists and scientists from national labs who come to visit us once or twice a year when we have meetings, and then some of them come individually at different times. And that's actually chaired by Bill Prindle, who was a local retiree. He's someone who retired from being head of research at Corning and now lives in Santa Barbara. And so that's a very useful vehicle for interactions. Then we have certain mechanisms for encouraging interactions with companies, and these are mechanisms which I essentially created myself. But first of all, I set aside some of the money in our budget for the center to support interactions with industrial companies in the areas of our main core research programs. And roughly speaking, we have about $200,000 a year, which is dedicated to that. And this is both an incentive and a reward mechanism, so that if my colleagues bring in support from industry for our core research projects, then I can reward them with some form of matching. And it may be about 25% match. It also helps when my colleagues go to companies to try to obtain some support, that they can say, well, if you give me $40,000, Tony Cheetham will give me another $10,000 from our pool of funding, and that helps as an incentive to persuade companies to support us. And we also have, in addition to our core research projects, we have a number of seed projects which we hope will grow into the core projects of the future. And again, we have an incentive mechanism for seed projects that involve partnerships with industry, and again in the form of matching. So we set aside another $100,000 or so. So altogether about $300,000 of our budget is set aside as an incentive to build interactions with companies. And then the other elements of our technology outreach include things like technology transfer workshops, which we've organized with colleagues from Princeton. We've had a series of workshops in areas of strategic interest to the nation, such as environmental issues, issues to do with computer modeling of industrial materials, and those have been very successful. And then finally, and I'll talk a bit more about this, we provide access to our facilities for companies from around the country. So that's roughly the sort of elements of our own interactions with industry. Let me talk about some of the models that we and other laboratories use, and I've tried to systematize them in as simple a way as I possibly can. And so, first of all, I wanted to talk about interactions that don't have any intellectual property issues attached to them, because intellectual property issues can inhibit interactions sometimes and make our lives more complicated. And we have a number of mechanisms that enable us to interact with companies without any intellectual property implications. And one of these is just to persuade the companies to give a gift to the laboratory. And there are actually quite a lot of companies that will give sort of small gifts to laboratories that have particular interest to them. And for example, you have funding for this workshop from the Ford Foundation, and we do approach foundations such as that. And one of them, for example, DuPont has a foundation, Corning has a foundation. These support research in the materials science area, and we approach these organizations to see if they will give us what's essentially an unrestricted gift based upon the fact that we, as a center, have quite a lot of rapport and levels of interaction with those companies. More commonly, we have gifts for individual groups, and this is normally it's individual professors who are going out to the companies and making the links, and of course they're interested not in supporting the laboratory in general, but usually, and we're all slightly selfish, we're interested in particularly in supporting our own research with such support. And so we, for example, we have a number of gifts from individual companies. In my own group, we've had gifts from Shell, Air Products, Mobil, and Unilever. And I'm going to talk about some of the work that we've done with such support. So these are not entirely unrestricted in that they're designated for a particular group to work in a particular area. But beyond that, there's no contractual interaction, so there's no intellectual property implication for it. And those work surprisingly well, in fact, and that, as the head of a National Science Foundation lab, that's my preferred mechanism for interacting with companies, because at the other end, we have the people at the NSF saying, we want to be quite sure that you're not using NSF funds to subsidize research in industry, and this can become a complication. And then we have occasionally fellowships from foundations, and we persuaded the Corning Foundation to establish a fellowship in a laboratory which would support a graduate student. And we call it the Corning Fellowship, and each year we run a competition and appoint a new person for 1 year. And one of the nice features of that is that the student who's appointed gets to visit the laboratory, the Corning Laboratory in New York, and make a couple of visits, and it's a very good mechanism for both exposing the student to a world-class industrial company, and at the same time it provides a nice vehicle for recruitment for the company, because they get to look at some of our very best graduate students and establish some kind of relationship with them. And we've been doing that for 3 years now, and a couple of the students who received that award have ended up going to Corning and joined the staff there. Of course, you can't get away entirely from, and nor would we want to get away from the possibility that some of the things we do can lead to important discoveries. And so we do also have grants, for example, for particular groups which would carry an intellectual property agreement. And of course, these are I don't want to go into detail of this because it's something that varies from one institution to another. It's a complicated issue. But in cases where we have a grant that's is essentially a contract, then there would be an intellectual property agreement, and there's also an overhead that the company has to pay on top of the grant. And so in Santa Barbara, at the University of California, the overhead on such a grant is 45%. So if I persuade a company to give me $50,000 for a project, then they're going to have to pay another $22,000 in terms of overhead. And what they get in return for that is some share in the intellectual property, some agreement about how long it will be before we publish our results. This can occasionally be a bone of contention. It can be an issue with companies. And they also, of course, are the first people to hear about the results of the work that they're supporting. So we have, we've had, in my group, a couple of these. We had one with Chevron, which was very successful and ran for 3 years. And then occasionally, and this is something that we've not done as a laboratory, but I'm working in Paris, as Yvonne said. I'm there for a year. And in Paris, the laboratory in Versailles, the Institut Lavoisier, has been looking at a global agreement with a particular company. And these are very interesting because they can involve a large amount of money. And so, they could involve $1 million or so for, say, a 5-year global agreement. The problem that has to be addressed is the extent to which you get tied up too much with one particular company and whether that serves the best interests of the laboratory. And right now in Versailles, that's a problem that we're addressing in relation to a possible agreement with a major French company. And also my colleagues at Oxford, when I was at Oxford, we had one of these agreements with Monsanto, between a particular laboratory and Monsanto, which ran for about 5 years, involved a very large amount of money, involved a lot of intellectual property agreements, and helped to build a brand new laboratory. And in a way, under this context, I'd include consultancies. And that's not an issue in a sense between the laboratory and the company, but it is an issue between the individual professors and the companies. And often consultancy agreements can lead to other relationships like grants from companies or contracts with companies. And I'm going to talk a little bit more about that later on, because there are occasions when, if you're a consultant with a company and you also have a project with the company that's supporting one of your students, that you can find yourself with a conflict of interest where you might know something that you are not able to tell the student who's actually working on the project. And this is something that's happened in my own group, and it's not a nice situation to find yourself in. Let me carry on just a little bit more with a third type of model, which is what I call the consortium model. And this has become, it's been very popular in the States, though it's now become somewhat less popular. And in this consortium model, a laboratory might get a small contribution from each of perhaps 5, 10, 20 companies who have a common interest. And just as one example that I picked, the University of Minnesota has a large consortium in the polymers area, mainly in polymers engineering. And that brings in a substantial amount of money to the department, to the center in Minnesota. And in return for the contribution, which is, I don't know, maybe $10,000 or $15,000 a year for each company, then the center has to provide some services for that, and they provide things like newsletters. They have regular meetings of the consortium, and this turns out to be a really good mechanism actually for enabling companies to interact with each other. because it brings together scientists from different companies who've got common interests, and it provides a good vehicle for those interactions. From the point of view of the centre, it's not a model I particularly like, because there are a lot of them already in the USA, and so it's quite difficult to start anything new, and also because they involve a lot of administration and workload on the centre in terms of servicing the needs of the consortium and all the bureaucracy and reporting and so on that has to be done. But as a kind of special case of it, there are quite a few consortia at some of our major national facilities. And during the course of this workshop, we'll be talking about things like synchrotron radiation. And certainly there are a number of consortia, industrial or industrial academic consortia that have been formed around major national facilities that help to support the instrumentation and the infrastructure for particular types of work. So, for example, there's a very large protein crystallography consortium at the Advanced Photon Source, which is the new synchrotron at Argonne National Laboratory in Chicago. And then also in the context of a consortia, I see some companies have developed their own consortia, and some of you might be familiar with Biosim MSI, which has developed its whole business around a consortium model in the area of high-tech computer software. And so there's been a consortium for polymers, which involved, at its height, about 50 companies, and a consortium for catalysis and separations, modeling of catalysis and separations. And so this consortium model, it can also be used as a kind of marketing model, as well as a model for interactions between academia and industry. So the last model I wanted to just say a few words about concerns access to facilities, because certainly one of the obligations in a way of perhaps a centre like ours, which has some very expensive and occasionally unique capabilities, is that it needs to make those facilities available to other people, whether that is people from other universities or people from companies. And so we make our facilities available to companies, and we have a charging mechanism for that, and so they pay the same as I pay for access to our X-ray facilities, plus the 45% overhead that the University of California charges. And then we also charge them, of course, if they're using our technical support, which normally they are, and so they would pay for the time of the development engineers to help them run their experiments and so on. And so we have a sort of quite a lot of local companies in Santa Barbara County, but occasionally companies from further afield who use our facilities. And we're quite isolated, just as you are in Sao Carlos. We're quite isolated in Santa Barbara, and most major American companies have other major universities nearby, and they're in the Midwest or they're on the East Coast. There's a problem that has arisen occasionally with use of facilities, which is that you can find yourself in trouble with companies that are doing this on a commercial basis. And so this is on the one hand, it's a nice mechanism for leading to interactions with companies, and often leads to other forms of interactions. But there have been a number of cases in the USA, and the National Science Foundation is very conscious of this, where commercial companies have sued universities for providing unfair competition because they don't charge commercial rates. And that's a sensitive issue. If a local company calls me as the head of our lab and says, "Will you help us to do something?" I am very reluctant to say, "No, we will not help you," because the next day it will be in the Santa Barbara news press that the university doesn't want to interact with the community. On the other hand, if I'm too generous in the way I help them, then I run the risk that we might get sued by a company that would normally provide this service for commercial rates. And so that's something we have to worry about, and you in the future might worry about here. Just to give you an idea, you know, like with our X-ray facilities, we're set up with each facility has a head, a director who will be a professor, and then some technical support, and then we have a lot of nice sort of X-ray powder facilities. At the moment we have 2 rotating anode sources, and we're about to get another one, and so we can do X-ray work for polymers, for ceramic materials, things like pole figures and residual stress measurements, as well as conventional things like powder X-ray diffraction and single crystal X-ray diffraction. We've got a nice range of software and so on. So we've got facilities of this type for X-rays, for electron microscopy, and for spectroscopy, nuclear magnetic resonance with liquids, NMR with solids, vibrational spectroscopy, and so on. And each of those facilities is organized in this kind of fashion. And it doesn't operate at a big level. The access to facilities is about 5% of our total business. But that's a bit misleading, because on some instruments it turns out to be 25%. There are certain instruments that our industrial colleagues are very interested in and they make heavy use of, and then other instruments that nobody is interested in at all. So, but as you can see from these lists, these are some of the sort of local companies that use our facilities, mainly local companies, who are sort of regular users of the facilities. And a number of those eventually evolved into more tangible collaborations. Let me say a little bit about national facilities, because this is where the, Sabato's triangle comes into play, when we're interacting with companies and we're also interacting with national laboratories. And so we as a centre make extensive use of neutron facilities, and a lot of companies are very interested in powder neutron diffraction as a tool, as I'll show in a few minutes. And so we have arrangements with both Brookhaven and NIST. Brookhaven is currently not functioning because there's a sort of major problem there, and so now we just have access to NIST. And then we use the synchrotron facilities both at Stanford and now at the Advanced Photon Source, where we've got a major project. And we use synchrotron facilities at Brookhaven as well. And we also use things like national computing facilities and the National High Magnetic Field Laboratory in Florida. Access to national computing facilities at the national labs turns out to be very difficult because of things like security issues. So we were using the supercomputer at Los Alamos National Lab, but it turned out to be virtually impossible to use it efficiently because they were not very interested in helping us to compile our programs, because they were mainly focusing on compiler problems related to the main mission, the sort of military mission of the laboratory. And so in the end, what we did was to improve our computing facilities in Santa Barbara. And they're now so good that some of our colleagues from Los Alamos come and ask us if they can use our facilities instead, because they're more user-friendly than the massively parallel machines in Los Alamos. So I'm going to talk a bit about science in a minute, but let me just review some of the pitfalls. You know, I've talked about the models that we use and some of the interactions. Just wanted to talk about some of the pitfalls that arise with academic industrial interactions. And I think the biggest one, compared with having a relationship with the funding councils like, you know, the National Science Foundation, is really the lack of continuity. And that's something, if you build new relationships with a company, I would definitely try to build some continuity into your relationship, because this has been a major problem for us. And of course, most of these relationships are quite personal. They involve interactions between individual professors and individual scientists in the companies. And then the scientists get moved to other projects, or they move to other companies, or they get promoted into the management, and suddenly there's nobody in the company who's interested in your project any longer. Or there may be a change of technical direction, which can sometimes be a nice opportunity and can sometimes be very frustrating depending upon how you see the change of direction. Or in the last few years, during the recession, we've had situations where the funding is simply being cut, because when companies are supporting work in universities and then life becomes hard, the first thing they can cut is support that goes outside the company. And that's understandable. It's difficult to tell your employees that they're going to be out of a job when you're giving money away to the University of California instead. And so this has been a major problem for us in the last few years. Occasionally, confidentiality becomes a problem, because it's difficult to, and in fact we're not allowed to do this, to put a student on a project which involves confidentiality that prevents him from talking to other people about his work. And that's a serious issue, because it can inhibit the student's progress, it can retard his career, and this can also happen with postdocs as well. And so I try, if possible, to avoid having people working on projects that are confidential. The problem is projects can become confidential because it's in the nature of materials science that you may discover something interesting and useful, and so a project that was fundamental can suddenly become a project that has some confidentiality associated with it, and then that's an issue that one has to address as best you possibly can. And related to all of that, of course, is the issue of publication. And as academics, we all want to publish our results as quickly as possible, and sometimes the companies want to publish them as slowly as possible. They obviously need an opportunity to secure an intellectual property position sometimes, and so we build these things into our agreements when we have contracts, and that's often a sort of major point of discussion. And then sometimes the consultancies can become quite a source of complication if you have a very close relationship with the company and you have projects in common with them. And so personally, I like to differentiate between what I do as a consultant with companies and the kinds of collaborations that we have for my own research group and for the centres, and keep these as separate as possible so that I don't have any conflict of interest. And all such relationships, at the University of California, we have a committee called the Conflict of Interest Committee, which scrutinizes arrangements such as consultancies and grants and so on. So we have to be careful about that. So let me move on for the last part of the talk and just give you some examples of just case histories of things that we've done over the last 5 years or so. And this is just in my own research group and relates to my own research area, but it's illustrative of the kinds of things that people in the laboratory do. I'll give you some sort of technical details. We had a very nice project with Amoco Technology on nonlinear optical materials, and which I'll talk a little bit about, and involving use of both synchrotron facilities, laboratory X-ray facilities, and neutron facilities. We had a nice relationship with Shell relating to zeolite catalysts, where we use the synchrotron. And we've had, and this is ongoing, a very nice relationship with Air Products in the area of air separation, non-cryogenic air separation, which you might find interesting. And just recently, a relationship with Eni Recherche in Italy concerning the determination of the crystalline structure of a new zeolite molecular sieve. And we've had a very nice relationship with Unilever in the context of detergents and detergency and cation exchange behavior. So I'm going to talk about each of these and just show you how they actually went. And most of them use sort of advanced methods in powder diffraction, which Yvonne referred to earlier. Things like use of the Rietveld method for refining structures from powder diffraction data, which I'll illustrate. More sophisticated things like combining X-ray and neutron data, powder data in structure refinement. Using resonance diffraction effects with synchrotron data, which enables us to get special sensitivity to particular elements. Using computational methods like Monte Carlo techniques for determining structures or simulated annealing, and then obtaining structures of entirely new and unknown materials, what I call ab initio determination of structure from synchrotron data. And these all sound very sophisticated and complex techniques, but they're all things that companies that we've been working with have been very interested in and able to take advantage of for problems of specific interest. So in the context of this nonlinear optical materials area, what we did was look at a whole series of nonlinear materials based upon potassium titanyl phosphates. And these are used for frequency doubling from, say, infrared to the green. So you can make a green laser by frequency doubling of an infrared laser, like a gallium arsenide-based laser. And so there's a lot of interest in these materials. And we worked with our colleagues, here's one of our joint publications, we worked with our colleagues at Amoco Technology, all the way through to sort of joint publications with Jim Kaduk and Richard Jarman, who were our collaborators there. And this was a relationship that went on for a very long time and led to some really nice papers where we were able to use simultaneously X-ray data and neutron diffraction data collected from argon to refine structures of materials in which we'd made substitutions, like made mixed sodium and potassium systems, to see if we could enhance the optical properties and understand the factors, the structural factors that impacted on the nonlinear optical properties. And in that case, for example, using this combined approach, we can show that the sodium and potassium are distinguishable, and they play different roles in the structure. So it's not a random solid solution. There's a very specific effect from using sodium and potassium. We can determine that directly from this joint refinement. So this is a sophisticated tool to, but something that the people at Amoco were very interested in. And then one day they phoned me up and said, we're not interested in nonlinear materials anymore. The management has decided that this is not the way we want to go, but we want to move away from frequency doubling to the possibility of making blue or green lasers using a different mechanism, which was upconversion, using upconversion technology. And so there are three different strategies here to make a green or a blue laser. One is frequency doubling with the nonlinear materials. The second is the wide bandgap semiconductors, the gallium nitride semiconductors, which now have become the most exciting area, of course. And then there's a third possibility. And so basically this interaction changed direction at that point because we had the capability to grow nice single crystals of these fluorides for upconversion lasers. And I won't talk about the details of that. If anybody's interested, I'd be delighted to. But we made some beautiful single crystals, and we obtained some very nice results on sort of optical properties of materials of that type. Let me move on to another area, which was the work we did with Shell using synchrotron radiation. Here we're using something which is even more sophisticated, which is the ability to alter the X-ray scattering of a chosen element by altering the wavelength that you use to do the diffraction experiment. And what happens as you go through an absorption edge with synchrotron radiation, this is something you could do at your synchrotron facility at Campinas, is that you can alter the scattering power of a chosen element by choosing a particular wavelength. This gives you fantastic sensitivity to elements that you choose to look at in this way. And my colleagues at Shell in Houston were very interested in being able to determine the locations of cations in a forgesite zeolite. This is a catalyst used for hydrocracking, and it contains both zinc and sodium, and they're interested in the distribution of the zinc and the role of the zinc in this particular system. This is a model system. This is not their real catalyst. There's a nice example of using the technology that we developed to demonstrate efficacy, and then they could go and use the same technique on the systems that they're really interested in, so that we have avoided any intellectual property issues. So we can determine, using this technique and using data collected at different wavelengths, we can pinpoint the distribution of the cations with incredible sensitivity. And this led to a nice paper, with the people from Shell, with Bill Reppert and Sunny Teng in ChemCom. So there was a happy outcome to this collaboration. We got a nice paper. They got some exposure to a new technique that they were unfamiliar with, and they then went on to use it in other types of problems. Let me talk about something that's still going on, which you might not be aware of, which is air separation using molecular sieves. Of course, most people would be familiar with air separation using cryogenics, where you essentially liquefy the oxygen, which has a higher boiling point, and so as you cool it down, you liquefy the oxygen, and you can remove the nitrogen. But you can also separate air using a molecular sieve, a zeolite, at room temperature. And this is really interesting because it essentially depends on the difference, not of the size, but of the difference of the quadrupole moment of nitrogen and oxygen. And the quadrupole moment of nitrogen is about 3 times that of oxygen. So if you use a molecular sieve with a small cation like lithium, then it will selectively absorb nitrogen at room temperature. And this has become a commercial process now. It's a major commercial process for non-cryogenic air separation. And it's increasingly taking the market away from the cryogenic technique. And it's a question of scale, that for very large scales, the cryogenic method is the best one. For smaller scales, but increasing scale, the zeolite method works. And it becomes very important to understand precisely where the cations are in the molecular sieves, in the zeolites, in order to determine how the systems work. And so we've done a lot of work in this area. I'm going to move on just quickly to show one example of it. Just recently, we had a nice paper with colleagues from Air Products, who we've collaborated on this, this is a joint synchrotron X-ray and neutron powder study of zeolite LSX. Zeolite LSX is a forgesite for people who know about zeolites. It's a low silica forgesite, and it's the state-of-the-art zeolite now for doing air separation. So we've continued to work on this project with people from Air Products, developing both the sort of techniques for doing this, like these nice sort of joint synchrotron X-ray and neutron powder refinements that are yielding sort of insight into the way in which the cations are distributed and how they interact with the adsorbed molecule, with the nitrogen. I just want to show one other example, which we did with Engie Recherche, where we've solved the structure of a new material using a computational technique. I was talking to Raul Lobo about the use of simulated annealing techniques to predict new structures. And Engie Recherche had a new zeolite structure which they couldn't determine the structure of. They knew it was a zeolite because it has nice adsorption properties and all the classical molecular sieve characteristics, but no structure. And we were able to use simulated annealing technique by taking information from powder diffraction, from nuclear magnetic resonance, and from adsorption studies to ultimately to obtain a crystal structure essentially using synchrotron data. So we produce a model computationally now, just essentially by brute force to produce a model that fits the powder diffraction data. And that's something that we're just about to write up. It's sort of at a late stage of development. I wanted to talk about these different things because I want to just take the final moment to look and do a post-mortem on where all these projects now stand. Because, you know, it's interesting to look back over the last 5 years or so and see what happened. And it's not always a happy story. Amoco Technology, they completely closed down all the optical materials work in 1995 when the new management took over and the new chairman of Amoco said, what are we doing with semiconductors and optical materials and lasers when we're basically an oil company? And they closed down the whole of the Amoco Technology division. My colleagues who were working on this project lost their jobs. They were redundant, you know, with no notice at all. And of course, we lost our project. And so that was a real shame. By then, we were working on the blue lasers, on the upconversion lasers, and that was very unfortunate. The work with Shell in Houston, that finished as well, because Shell had a rationalization, this Shell company, and they decided that the research and development company, research and development should, from a couple of years ago, would be Shell Development Company and wouldn't do any research. And so our relationship with Shell in Houston finished, and happily what happened was that we managed to continue our relationship with Shell in Amsterdam with the main research lab. So we still have some funding, we have a collaboration there. But the interaction with the people in Houston disappeared. The non-cryogenic air separation work, that's continuing with Air Products. And the funding's very, very low, but the relationship is really good. And so we're still working with them. With Engie Recherche on finding new structures, we're working with them. There's no intellectual property, there's no funding even. This is something that we are sufficiently interested in that we would do it for nothing, because it's nice to have the challenge of new materials to offer up as challenges for the techniques that we're interested in. The work on zeolites, which for detergency, which I didn't talk about, that's been a bit of a disaster too, because earlier this year, Unilever decided to sell all its chemical businesses, including Crossfields, which makes these zeolites for detergency and for catalysis. And so all the people that we were working with were either redundant or they were assigned to new projects, and the company ceased to be interested in supporting external work in the parts of the business that they were selling off. And so that relationship has terminated abruptly. So some of these things have worked wonderfully well. Most of them have worked well for a short time, and then circumstances have changed. And that's why I say that continuity is the problem. But I want to end on a positive note and just say that my experience has been really good in terms of approaching relationships with industrial laboratories as real partnerships, and partnerships not of just having funding from the company and doing the research at the lab, but having partnerships at a technical level with the scientists in the companies. And that's enormously enriching for us as a center to have the intellectual input from the companies and to expose our students and our postdocs, and indeed ourselves, to the knowledge and the intellectual capabilities that the companies have to offer. And so my theme for industrial interactions between companies and universities is really one of partnerships, and to look at these things as real partnerships, and under those circumstances they tend to work extremely well. So thank you very much.
Thank you very much for a wonderful talk. We'll have opportunity to discuss the debates. The next speaker is Dr. Hendrikus de Waal, which will be introduced by Professor Zanotto.
Thank you. Nele, né? Está aqui. Thank you, Professor Mascarenhas. It's our distinct pleasure to introduce Professor Hendrikus de Waal. He is Professor of Glass Technology at the University of Eindhoven in the Netherlands. He is also the coordinator of all technical committees of the International Commission on Glass. This International Commission has about 25 technical committees, and he is the chairman of all of them. And in addition, he is also the chairman of the TC23, the Technical Committee on Training and Education on the Glass Industry. He is formerly, he was a director of the TNO Institute of Applied Physics in the Netherlands, head of the Glass Group, and he also is a consultant for several international glass companies. So overall, we couldn't think of a person with a better profile than Professor de Waal. And last but not least, he is also a very nice person, and that's why we invited him. So, Professor de Waal.
He's going to connect the channel, I think. On. Já está, okay. No,
it
no,
works.
it's okay.
Thank you very much for those kind words, Edgar. Of course, I didn't know I was such a nice person, but and I'm very happy also to be here. It's not my first visit to Brazil. It's not my first visit to São Carlos. It's already the second visit this year even. I must say, up to now, the weather has always been better than this time. It even gave me some sore throat, so I'm very happy that the organizers gave me this instrument, not only because I don't have to speak so loud, but also now I have two hands to handle my sheets. And the first speaker only had one, which also always gives a little bit of logistic problems. So the subject I'm going to talk about is basically the research and training on glass in the Netherlands. But to do that, I will start at a little bit broader subject on the organization of research in general. Anyway, it will turn out that in the Netherlands there has been developed through the years a cooperative approach between the universities, industries, and TNO. So the first thing I have to do is to explain to you a little bit about the TNO organization, what it stands for, and so on. But before I do that, let me say a few words in addition to what Professor Cheatham has already talked about. I must say I was impressed in the way he did that, quite open and honest about not only the good points, but also the points that are not so successful. And also he mentioned a number of pitfalls, and I want to add something to that. Because if you talk about cooperation between industry and university, it seems so logical. I mean, industry needs know-how, and the university develops know-how. So why doesn't it always work? It works sometimes, but it doesn't work always. Well, some of the problems have already been mentioned by the first speaker. I want to add some. First of all, there are different missions. The university is there to educate people. That's their mission, educate people. And their R&D can help with that. But that is very important. The industry, on the other hand, they apply knowledge to sell more or better products. So the issues are quite different. Which means also that sometimes the university will develop knowledge that is not of primary and first interest of the industry, because they need it for their education of the student. A second problem can be what I call the language barrier. Scientists and managers do not always speak at the same wavelength. They don't speak the same language. This is especially true for what we call the SMEs, the small and medium scale industries. They have to think on another time scale. They have an interest of what to earn money tomorrow or even today, and not in 10 years from now. Whereas a scientist thinks on a much longer time scale. So they can have a different wavelength of communication. There may also be a conflict of interest, and that was mentioned by the first speaker in a little bit different way. I put it here a little bit bluntly, that company scientists also want to do nice work. They want to do research. And they will not always like it when the nice work is done by the universities and they have to do the troubleshooting for the factory only. This is to say, of course, it is a little bit more subtle than that, but a conflict of interest may occur, especially with the larger companies who have their own research laboratories. There may also, on the other hand, be a lack of interest. Not all university professors and scientists have an interest in typical industrial problems. So, some 60 years ago in the Netherlands, the government already saw that the cooperation between the universities and the industries was not as it should be, so they decided to establish, 60 years ago, another organization which they call TNO, which stands for Organization for Applied Research. And that was to be placed between the universities, the government, and the industry. Instead of government, you could also read society. Yeah? Typically in between those three. And the mission of TNO was, of course, quite a different one from the university. TNO aims to increase the competitiveness of industry and to assist governments with policy formulation, implementations, and so. So they do strategic research. They do, I have to be a little bit careful with that. Applied research, not the fundamental research so much, and they do consultancy. In the Netherlands, TNO has over 4,000 employees, so it's certainly not a small organization. 41 of those 4,000 have a university training. 47 of them even have become professors. Well, where does the money come from for TNO? There are three main segments in TNO. The first one is the industrial technology division, which is for us the most interesting. 73% comes from contracts, either with industry or can be with the government. 27% is funding from the government. For health, of course, and prevention, prevention, it's a smaller group. The turnover is 64 million Dutch guilders. If you divide these figures by 2, you have it in US dollars. And there, of course, because it's more like a society issue, the funding from the government is considerably higher. And for the defense research, of course, it's even more than for health. Defense seems to be more important than health. When you look at TNO in general, this is an interesting way of looking at it. What are the markets for TNO? This is the year 94, but it has changed a lot in the past. But recently it is more or less stable. You see that the government gives 25%, foreign contracts 20%, so TNO does not work only for the Dutch industry anymore. 20% comes from foreign contracts or from international organizations. And it is interesting to see that only 10% comes from the large companies, multinationals, or the companies that have their research in the Netherlands, like Philips, Shell, Unilever, and companies like that. But that's only 10%, and 40% comes from the small and medium-scale enterprises. And that used to be the other way around, let's say, 20 years ago. And why has that changed? That mainly because the government gradually reduced the university budgets, so the universities were forced, because they wanted to have the same budget as they had before, to work more with industry than before. And that were mainly the large companies, because that is the relatively easy way of communication between the scientists in the large companies and the universities. So TNO moved to the market of the small and medium scale and enterprises, because that was still an open market for them. And that didn't occur overnight, of course. It takes many years. Also because you have to learn to speak another language, one of the problems I talked about before. So that's about TNO and the situation in TNO in general. Now I come from one of the institutes in TNO, and there are about 15 of them, which I will not even try to mention all of them. This one is the one I come from, TNO Institute of Applied Physics, which stands, the Dutch abbreviation is TPD. If you want to look them up in the internet, you would either look to TNO NL. NL stands for the Netherlands, of course, World Wide Web, of course, and so on. And if you want to go in, you need to know that Institute of Applied Physics is in Dutch TPD. So you need TPD, TNO, NL if you want to find them. If you want to find the web page. What is TPD? What is their assignment in addition to the one that is in general for TNO? Well, they do basically, of course, R&D in applied physics. That's why it's called Institute of Applied Physics. But they do so very much jointly with the Faculty of Applied Physics in Delft University and Chemical Engineering in Eindhoven University. And that is a little bit different between the rest of TNO and TPD. I said TNO moved to the small scale industries a lot, small and medium scale. That's also true for TPD, but they have always, from the beginning, and the beginning dates back to 1941 or 1942, that was the year that TPD was established. They have always very much worked together with the faculty. In fact, they are located in the faculty, as in those two faculties, TPD. So they are used to utilize the results of the university research. And that is mainly what I want to talk to you, this approach of doing this together. Not the way that the university does the work for the larger companies and TNO for the smaller companies. No, this typical approach of the Institute of Applied Physics. Contracts are on a non-profit basis from industry, government, and other clients, of course. So TPD sees itself in this way, more or less. Like here is the university, and here is the industry, and TPD tries to be a bridge between those two. Some people say, no, we are not a bridge, we are the vehicles moving up from here to there. And I think a little bit more dynamic. So there's close ties with those two universities, and this collaboration with the university exists through the Science Council. The professor in the faculty form a kind of advisory board for the institute. There are a lot of PhD students, and of course the laboratory facilities that are used jointly, and there may be joint projects. Now joint projects, that means usually that all the administration work and all the writing of proposals and so on is done by TNO people, not by the university people. All people like that. The industry likes it because TNO is used to do these things, and usually the university scientists also like it, that this burden is taken away from them. Some core data from the year 1996 for TPD are interesting, is that here in our case the foreign industry amounts to 18%, which is higher than for TNO in general, and the national industry to 37%. And then, of course, you have public funds, about 23%. That's the money that is basically free for us to use for purposes that we think that are fit for our purposes. The turnover is about 77, let's say almost 40 million US dollars. And we had in the year 96 positive results of about $2.5 million. Which we are not supposed to make. I mean, we are not there to make a profit, but it's nice to have a profit now and then. Then in the years, some years you have a negative result, you have some money. I want to spend the rest of the time that we have for this talk on the subject I'm most familiar with, the materials division of TNO, of TPD. But before I do so, let me show you. It was already here, but I forgot to show it. I only talked about the money up to now, but not about what we do, spheres of activity. There are a number of things all connected to physics, and they are the divisions of the institute. In total, like you see, there are almost 400 people. 50% of them have a university degree. The divisions are systems and processes. That's mainly computer simulation of processes and systems. Acoustics, optical instrumentation, that's usually electronic, materials, and then there is an evaluation center for instrumentation. I'm not going to talk about all of these. I'm only going to talk about the materials division, which is located in Eindhoven, and it's the only one located in Eindhoven. So this number, 56, was in 1996 the number of people working on materials in TPD. Now materials is not specifically a physics subject, of course. So the word applied physics nowadays is not completely. That's my fault. I started this materials division because I'm a material scientist. Nowadays in the material group we do not have only physicists. We have physicists, but also chemists, technologists, and mechanical engineers, geologists. And that is, I think, one of the strong points, that you have this multidisciplinary approach. The materials that we study are the traditional ceramics, technical ceramics. We have a department on glass technology, mainly glass manufacturing. There is one on glass products, material properties and things like that. And there is a department on inorganic materials chemistry. I'll say a few words about this. Skip all the information about TPD in general, because that's not really the issue for this paper, unless you have an interest in it, but then we can do it during question time. I want to say a few words about the different work departments, mainly to talk about what is the cooperation with the university in those fields. So let's start with the advanced ceramics development, processing, and applications of advanced ceramics. You see what the expertise and the typical application. And all I want to do is to tell you what the relation to the university is. We have created a center for advanced ceramics together with one of the university groups in Eindhoven University. It's an official center for advanced ceramics. And there is a scientific director who is the professor who is the head of this department in the faculty of chemistry. And there is, let's say, a managing director who is the head of our department of advanced ceramics. So it's a joint effort. All the people working in the university and in this T&O department belong to this center, as long as they work on ceramics. If in the faculty they decide suddenly someone does something outside the area of ceramics, he does officially, for that period of time, not belong to the center. So some of these things are done by university, and some of the things are done mainly by T&O people. And always there are a lot of PhD students. Mechanical modeling is one good example, for instance, that is mainly done by PhD students. Now, in fact, in the department for the traditional ceramics, this is somewhat different. It's mainly about processing and kiln technology. And the subject, there is not an official cooperation with one of the groups in the university, but PhD students in several groups in the university are doing work together with this group. For instance, on the mechanism of drying of clay materials. From the material side, what happens when the water molecules come out of the clay? How can you avoid cracking and things like that? Has been done by a PhD student. On the other hand, the same for sintering, by the way. Also, when a PhD student has worked on modeling of all the flows of the air that is necessary to dry the products. That's another PhD kind of work. So usually we define a project which has an applied part that's done by the TNO people, and a more basic scientific part, if that is possible, of course, which is done by a PhD student. You have to make an agreement with the industry that they agree that that part will become public, the one done by the PhD student, of course, because he has to write a thesis. The other part can be confidential, and the TNO people use the knowledge that is developed by the students for this applied part of the project. In the Department of Materials Chemistry and Coatings, there is a very strong cooperation with the university, but not only with the university in Eindhoven, very much with other universities in other parts of the country, because this expertise is not available only in Eindhoven, only partly, so we have a lot of cooperation with other universities as well. I will not go into details about all these typical applications. I'll mention PhD work done in the field of electrochrome coatings, and nowadays a lot of work is done on hybrid coatings for protection of steel and other materials by the university people together with the TNO people. Then there was this department which is called Glass Products, which includes expertise and work on testing, characterization, glass products like containers, double glazing and things like that. That's not so much a university issue, testing. So that's done by TNO people. Although I must say that in the field of developing impact testing for container glass, that work, for instance, was done by a student. In fact, it was done by a student which came from Campinas, and it was a joint project between Professor Zanotto and myself to do this work some 7-8 years ago. So it happens, but it is not a common thing that students are involved in that. Much more so in the field of, for instance, radiative heat transfer and optical properties. There, students are involved in developing new methods or new techniques to measure. For optoelectronic glasses, this is basically developing of active glasses for optical amplification and things like that, rare earth doped chalcogenide glasses and phosphate glasses, things like that. That is, well, that's one of my hobbies. I'm a physicist originally, and although it did not become my main line of work later, it still remained one of my hobbies. So this was mainly done in the time that I spent in the university. I should perhaps have explained a little bit better to you that I had two functions up to a few years ago. One, I was the manager of this whole group of materials. And managing, that's not research, that's administration and finding money and things like that. But in addition, I was a part-time professor in the university. I still am. And one of the things that I did there was with PhD students work on these optoelectronic glasses. Now this is a sensitive subject. Companies, it has been mentioned, can stop the cooperation from one day to another because they think it's either too important, so it has become a core issue and they want to do it themselves. Another reason can be that they say, what the hell are we doing? This is not our field. We make, I don't know, windows or something, so we are not going any further in this field. Well, this is what can happen, so we have been always very careful not to include too much TNO time in this area, only to accompany students, PhD students. Nevertheless, we have done some very nice results. Recently, we developed a very good new optical amplifier for planar waveguides, which is now being implemented in industry by TNO people from this department. So it's now reaching a state where TNO takes over, but up to now, up to, let's say, 1 or 2 years ago, it was mainly a university issue. So that there, university had the lead In most other subjects, it's TNO that has the lead. Now, I want to, the rest of the time, I want to talk about the last department that I had to mention, that is the glass technology department, and that is working on glass melting and furnace technology and so on. Expertise is in melting, furnace technology, melting kinetics, homogenizing, glass quality, melting process, doing measurements and things like that. And it has, of course, a lot to do with energy conservation, emission reduction, primary methods, not the development of filters, but primary methods, changes in the process for reduction of emissions, defects, redox, gases in glass, foam, refractory, you name it, everything connected with glass making, including tank design and things like that. That's what the department tries to do. And I must say, we started this work about 1982, the time that I became a professor in the Eindhoven University, because I was there mainly for teaching in glass technology. And I spent there at least 1 day a week. And I was teaching students a few hours in the morning, and after that I thought, what the hell am I going to do the rest of the day? You can talk to your colleagues, but they don't want you to come every week. So I said, I have to find some new research here in Eindhoven, not in the place where my institute was, in Delft, which is about 1.5 hour driving away. So I have to do something here. Now the industry, so I talked to the glass industry about that, whether they would be interested, and they said, well, maybe we're not so sure. So it was not a situation from a push from the industry to start to do that, but nevertheless, I did it. And we started with doing some work in the area of emissions. How can you understand what happens to flue gases which contain contaminants from the glass when it cools down thermodynamically and kinetically? It's basically, it's fundamental work, and it's very interesting, and it has become, of course, very interesting for the glass industry. But in that time, they said, no, please, we don't want the government to understand that we have a problem. So please be careful. 2 years later, that was completely finished. The government had understood that there was a problem anyway, so they wanted to solve it with our help. So we were lucky to have chosen the right subject. But this is sometimes how it works. You have to take a risk, and you have to choose a subject that you hope that in some years will become an important issue. Nowadays, we try to understand all the basic mechanism of the glass melting process. And this is just a way of explaining what kind of problems and what kind of issues there are. And the flue gas chemistry, like I said, was one of the first to tackle. You can also say it in another way. Let's say this glass technology group, what do? They do chemistry and physics of glass melting by laboratory simulation. So there's a lot of furnaces and measuring equipment and so on. That is a very important type of work, which is mathematical modeling of the complete industrial glass melting process. Actually, that was the second subject that I chose for this new group in Eindhoven after I became a professor. That was also 1983 or something like that. And also that was not really because the industry wanted us to do that. It was because we ourselves thought that is going to be an issue in the future, perhaps. Industry was more like, well, that's nice playing around with computers, but we don't think that will ever become an important issue. Well, it has become an important issue. Nowadays, we make a lot of money with that. But it started very, very modest. It started with industrial cooperation, but the industry, at least the main contributor, the man I knew and who was interested in this work, he told me, please don't tell people that I give you money for that, because my boss doesn't want that. So we had to give it another name, and that was the first few years until this boss retired, we had to start it. Well, I shouldn't tell you that, so forget it, please, but this is, fortunately, I didn't mention the name of the company. That's how things sometimes start. You know someone, you find out at some reception that you have a common interest, and you start to do things on a very modest scale, and if you're lucky, it can grow. So the basic research from the Eindhoven University in the field of modeling comes in, and in the field of laboratory work, analysis of industrial glass melting processes, measurements in glass furnaces and things like that are included. Measurements in glass furnaces are usually not done by students, of course, but done by PhD people. Now, how do we work in general in this group with the glass industry? Now, the glass industry in Holland, just briefly, there's an annual turnover of, let's say, $750 million US. That's to give you an idea of the size of the glass industry. 27 furnaces, that's the total in Holland. And mainly it's container glass. There's one float glass plant. Well, you can read the rest yourself. So